Okay, so thank you. It's my pleasure to be here, my first time here. And I will be talking about essentially what I've been thinking about for the last 10 years with myself and my collaborators. Maybe I'll give a little small introduction on the blackboard before I start to flash the slides. I have a PDE background, but I like thinking about problems that are motivated by probability and mathematical physics. And so slowly over time, I've become more of a probabilist. But still, I like to approach the questions from an analytic point of view. So the thing we've been doing for a while is to try to understand, just for an elliptic operator like this. So I have an elliptic equation like that, divergence A grad U equals 0, where A is somehow elliptic, which means its eigenvalues are positive and bounded. I want to understand what this equation is doing on large scales. So often when you're an analyst, you take a PDE and you zoom in and look at small scales because maybe you're interested in questions of regularity, and that's an issue of a small scale. We want to do the opposite. We want to kind of zoom out and look at what's happening on a large scale. And what that means, or the way that we're approaching it, is you imagine you have an equation in a big box, and we would like to somehow coarse grain the system. So maybe the field A of x from the point of view of our large box is very complicated and has many, many scales and oscillations and degrees of freedom and so on. And we want to somehow understand the effective behavior. So so one idea is you cut the big box into smaller boxes. And for each box, you kind of want to look at what the field's doing in that box, look at what the solutions, how they are behaving, and kind of replace the field A of x with maybe just one matrix A of the box, which kind of represents the field in that box. This is may seem like a bad idea because you're deleting a lot of the information, and that's bad, but it's also making the equation simpler. And in the extreme version of this, where you kind of zoom out to infinity and look at one matrix for the whole field in all of space, this is known as homogenization. So, which is a whole field of, sort of subfield of PDE. And so we are kind of doing, we have developed techniques for homogenization, but now we're trying to sort of use them in a kind of intermediate regime where you don't have homogenization, meaning that the equation, when you zoom out and look at it on a large scale, doesn't look like just one, an equation just with one constant matrix. We want to look at situations in which you have many, many scales, and you need to kind of develop a kind of description of the system which is scale dependent. So you can have a mesoscopic description all the way up to the macroscopic scale. That's sort of the general idea. And I'm going to talk, though, about a very specific situation in which we can do this. Okay. And please stop me if you have questions. I know it's kind of a broad audience talk, but if you want to interrupt me, I'm happy to be interrupted. Okay? So, this I forgot. Okay. So the equation that I actually am looking at, and I'm going to give a kind of probabilistic description of the problem before later switching it to a PDE, is this stochastic differential equation. So I have, so there's a lot of stuff written here, but this second term is a Brownian motion multiplied by a very small parameter. You should think of the parameter nu as being in 10 to the minus 12 or something very small. You have a vector field here, F, which is sort of advecting the particle. It's pushing it around. If there was no Brownian motion, this would just be a simple ODE. If there was no vector field, you would just have Brownian motion. And so the interesting thing is to have both, of course, but this is, of course, a very general stochastic differential equation. And so I'm going to tell you what features I'm interested in, I'm going to give F some properties. So I want the F to be a bit noisy. So in fact, F is going to have, it's not going to be like a smooth function with kind of one characteristic scale on which it varies. I'm going to make F have wiggles, and then smaller wiggles, and smaller wiggles, and it's going to have wiggles across a large number of scales. Okay? So that's first, and it's going to be itself random. So I have two sources of randomness going on. I have randomness in the sort of Brownian motion paths, which tell me which of the which of the paths my SDE takes. But I also have randomness in the choice of the vector field, which kind of is the first randomness. You first choose the vector field. You You roll some dice, it chooses a vector field for you, and then you look at the paths of the stochastic differential equation, okay? So I denote the law of the vector field with the math-BB LaTeX symbol, okay, and the expectation as well. And the trajectories of the process I denote with the boldface symbols. They get superscripts because you have to know where you're starting. The x0 is like the starting point where this thing starts at time 0. And the f, you also have to know which vector field you picked, okay? And we're interested in what happens on very, very large scales. So you can either think about putting a lot of small scales into the f and making it kind of rough, or you can think that f is actually C infinity smooth on the unit scale, but has many, many large scales in it, kind of if you're zoomed into the microscopic scale. And then you want to understand what happens to the process at large times. And this is the perspective that I'm going to take. I'm going to kind of assume that everything is regular on the unit scale. I really don't care about, like issues of regularity. I care about what's happening on super large times. Okay? I keep forgetting that click doesn't work. Okay. All right, so the particular model and the way that I'm thinking about the problem was already considered by physicists in the 1980s. There was a series of papers by theoretical physicists. I think the best one was in like 1990, so it was basically done by them, then from their point of view. They split into 3 cases. There's the case in which f is a potential. There's the case in which f is incompressible or divergence-free. And any vector field can kind of be split into a divergence-free part and a potential part. Those are kind of, it's an orthogonal decomposition of sort of L2 vector fields. But you could also have the case where you don't remove one of the parts. So there's the potential case, the divergence case, and the kind of both case. And I'm going to be mostly talking about the divergence-free case in this talk, so the second bullet. And so what did the physicists do? They used what they call renormalization group arguments to predict the large-scale behavior of the process. They have some way of doing a kind of heuristic coarse-graining invented by, I think, I'm going to say this wrong, so I'm not going to say who, but it was invented by physicists in the 50s who were trying to understand things in quantum field theory, but now is a kind of very general tool that physicists use for many things, including things in statistical mechanics and in statistical physics, and this is really a statistical physics problem. When the physicists wrote the first papers about it, they considered also the second bullet, and they said, this is kind of a toy model for a turbulent fluid, okay? Because they're not just going to pick any divergence-free case, they're going to make f be a random field that has certain properties, and they say that this is their toy model for a turbulent fluid. The reason they think it's a toy model for a turbulent fluid is that, okay, you have it's a turbulent model for the behavior of a tracer particle in a turbulent fluid. Like you imagine a small particle of pollution getting, moving in wind or something. Because in a turbulent fluid will be divergence-free and will advect the particle. But the particle will also be bombarded by random, sort of air molecules, and so there will be a Brownian motion component to it as well. All right. So this is the sort of background. The exact behavior of the system will be really determined by what? So if I pin down, say, the second bullet, what else do you need to know? Well, you need to know the law of the f, like what the f is going to do, what its correlations are, And so if you assume f is a Gaussian field, which is what the physicists do, and that's sort of the canonical example, then what matters is the covariant structure of f. What really matters is how the correlations of the f decay. So like if you look at f at x and f at y, how correlated are they when x and y are going apart? And that's just another way to say, what is the size of the sort of large, of the low Fourier modes? Like how strong are the large wavelengths in the problem? Because if you're supposed to zoom out and see something at a large scale, then if the f itself has a lot of low frequencies, large scales in it, then that should be interesting for your problem. Okay. So what the physicists do is they write down that they sort of write down this covariant structure. They say, let's assume that f is a Gaussian field. It's isotropic, so there's no preferred direction. If you make it anisotropic, it becomes crazy. It actually isn't impossible to analyze. So it's not just an assumption of convenience. So they assume it's isotropic, and they assume its covariance is decay like this. Again, I'm not worried about the singularity at x equals y, because everything is smooth on scale 1, and so this is not happening. So just imagine x and y are only, they're bigger than 1 from each other. So the question is how this decays. And the interesting transition happens when p is 2. So if p is greater than 2, then there's not enough large-scale behavior in the f to cause anything interesting to happen. If p is equal to 2, then something kind of borderline interesting happens. And if p is less than 2, then something much more interesting happens. And I'm going to explain what, and this is observed by the physicists. The special case is in dimension 2, when the field is the perpendicular gradient, grad perp of a particular random field called the Gaussian free field. And this, in that case, it corresponds to p is equal to 2. Just so you understand what I mean, I think this notation is not standard, so some people have never seen it. This thing just means you take the gradient and you rotate by 90 degrees, and then it's divergence free, right? So it's minus the y derivative of h and then x derivative of h. Okay. Okay, so more generally, let's see, so what did I say? The Helmholtz projection of white noise onto divergence-free fields corresponds to p equals 2. So if you take just like a white noise, and then, okay, you mollify it on the unit scale or something to make it smooth, so it's kind of a smoothened white noise. And then you take that thing and you project it onto the space of divergence-free fields, then you'll get p is equal to d. Okay? But p is equal to 2 is critical. So in that sense, dimension 2 is critical. So here's what's supposed to happen. And this is, again, happening in any dimension, not just dimension 2. Because the parameter p corresponds to the covariance decay of the f's. But this happens in every dimension. OK, when p is bigger than 2, then what happens is you get diffusive behavior. It's as though the drift is not there. So remember, I'm going to write here the equation. So you have this drift, and you have a little bit of this diffusion. Okay? And one way to measure kind of how much disorder is in the system is to ask, what is the variance of the position of the particle at time t? Okay? And I just kind of project the variance here by just saying, well, how far from its expectation do you expect it to be? But notice that I'm putting here a kind of variance only with respect to the process. I'm not taking the variance with respect to the f. So it could be, for example, that f has, f points in one direction like this and pushes you to the right, in which case this mean will not be 0. Okay, so what this is really asking is, what is the uncertainty in the particle's position at time t? And if there was no f, the uncertainty would be the variance, that is, would be 2 nu t. And you take the square root to get the standard deviation, and you get the square root of t scaling. That is the diffusive scaling. So that's what you would expect. This is what Brownian motion satisfies. And if the correlations decay fast enough, the f will affect the constant that goes in front of the t. It'll change this 2 nu to something bigger, because the divergence-free flow will kind of enhance the diffusion in the same way that when you stir your coffee, the milk goes into the coffee more quickly, and so it'll enhance the diffusion, but it won't change the scaling of t. If the correlations are slow enough, if p is less than 2, then suddenly the scaling is changed, and it becomes super diffusive. The exponent of t is now bigger than 1, and they have an exact prediction for what the exponent is. Actually, they have a different prediction. Their prediction's wrong, and then we thought that we had caught them in something wrong, and then we found a later version of, they have some lecture notes they published later, and it's correct. So we were a bit disappointed. But anyway, in the case p equals 2, which I'll spend most of this talk talking about p equals 2, because that's the case where there's already results that are actually on the archive. You're kind of in a borderline situation between these two. So you should expect, okay, maybe there's some logarithm. And yes, there is a logarithm. It turns out that the diffusive behavior is corrected by the square root of log, okay, which would be hard to see in a kind of even in like a numerics experiment, but it's there. So, all right, so any questions about that? Is it clear? Yeah?
What is the covariance of not stochastic values?
But F is stochastic. So there's two sources of randomness. First, the F is random, and then once you have like picked F, then the paths are also random. So it's like a doubly stochastic problem. Yeah, and so this, there's a, thanks for the question. Yeah, so you have to keep both in your mind, and when you look at theorem statements, you have to ask yourself which expectation are they taking, because it actually matters. Yeah. So this thing is really, once the F is chosen, what is the uncertainty in the position of the particle? You could also then take the expectation with respect to the F, with the, which is the fatter kind of blackboard bold E. And that would be the expectation of the F. Okay. Okay, so here are the physics predictions. Sometimes I skip this slide. Okay, so there are some details about how exactly they do it. The first prediction, so there's two kinds of things that there's, I'm going to explain these buzzwords very quickly. There's this buzzword annealed and buzzword quenched. Those are different. Annealed and quenched are kind of in opposition. It comes from metallurgy. But what annealed means in our context is you've taken the expectation also with respect to F, which is, in this problem, less physical. Because what you really see is a random vector field, and then you want to know where the particle goes. You're not going to average over all vector fields. Okay, that makes sort of less physical sense. And the quenched result is saying we want to know for like, you know, we want theorems that say for almost every realization of the random F what happens. So if you can prove quenched results, then in one line they usually imply annealed results. You just take the expectation. But it's often very hard to get from here to here. And the quenched results are maybe like, you know, typically about an order of magnitude harder to prove. Okay? And now, I want to explain what causes the superdiffusion to give you kind of picture in your head about what our stuff is about. Okay? So let me try to draw a little picture. And I have a little video I can show you. The reason that the superdiffusion happens, you may think, well, as time goes along, the particle somehow speeds up. But no, the coefficients in the stochastic differential equation don't depend on time. So if it's a Markov process. So if you run this for 1,000 years and stop and then start running it again, you're going to see the same behavior after 10,000 years as you saw originally. So what is causing the superdiffusion? It's because the particle looks, it behaves differently at different scales. At certain scales, it looks like a diffusion process with a larger variance than it does at other scales. Okay? And the reason that this happens is because, okay, I mean, if there's any randomness at all, it has to come from the original diffusion, right? If I take this away, my equation is deterministic. Even though the F is random, there will be no variance, right? At least no quenched variance, because this is just a deterministic thing. So all of the uncertainty has to come from this. On the other hand, if this wasn't there, then the uncertainty would be just that, and that's much, much less than the t that we can have if we have superdiffusion. So therefore, all of the uncertainty must come from that. And so you're kind of asking, okay, but who does it actually? And the answer is that there's an interaction between the two. Okay? The diffusion plays a role of kind of destabilizing the trajectories of the ODE. The ODE is going to actually do it, but the diffusion is going to kind of, you know, you're going to reach a decision point where you're not sure should you go left or should you go right. And if you go right, then you'll go way over there. And if you go left, you'll go way over there. And the diffusion will just make a little tiny bump to make you go from one to the other, like if you're on the top of a hill or something like that. Okay? And so one way to think about this and see it in front of your eyes is to think about the periodic cellular flow. I don't know how well you can see that from all the way back there. But this is supposed to be a vector field that is kind of having swirls. So I'll draw a picture of it here. Okay, and so it's just going to repeat periodically, and the vector field in this cell is going to go, I guess, counterclockwise, and in the next cell it's going to go clockwise, so that kind of these streamlines kind of match up. Okay, and in this one it's going to go this way. so that these streamlines kind of match up like this. And then in this one, it's going to go like this again. Okay. All right, so let's imagine that we tile the plane with such little swirls, and that we let the ODE go. Well, you're just going to follow those closed streamlines. It's going to go in a circle. You're going to have no variance. Nothing will happen. But imagine you put a little bit of diffusion there now. What's going to happen? Well, you're going to start, maybe you start here. You'll kind of go in circles, but maybe you'll with a little bit of randomness. And finally, the randomness will put you kind of on the edge of the square. And what can happen is you can cross into the nearby square. And if you do that, you see in this square, it's going, let's see, so it's, actually I did it backwards, but it's going against the flow here. But in the nearby square, you'll go the other direction. Instead of going this way, you'll go that way. And now you're really apart by O of 1 if this is size 1, whereas the diffusion might be 10 to the minus 12. So right on the edge of the boundary between the two squares, you can find yourself diverging. And I have a movie for this, which is fun to show. So let me try to show it. So what I do in this movie, this little simulation, is I release like 20 different of these diffusions in exactly this setup. So you're going to see 20 of them at once, and then you're going to see the trajectory of their flow. And you see slowly, like, that guy up there is getting caught kind of in a little cell. But this orange thing took off and went far away. It really went far. And so you see them, you can kind of see that they do almost random walks on the edges of the square. So they get stuck inside of a single cell for a while. If they get to the boundary, then they can do a random walk on the it's almost a random walk on the lattice, you see? And then they get stuck again. So because of this random walk behavior, the little bit of diffusion can kind of make them go far, because the uncertainty that you get in the particle's position due to this random walk is much, much, much larger than the original diffusion, so you have a kind of boost. Now what can happen is that this is just one scale of the vector field, perhaps. I said that I want my vector field to have many, many, many scales. Maybe the vector field does this, and there's a boost from the very small scale here to the scale of this kind of lattice. And when you go to a larger scale than the lattice, you see this random walk as being, again, like a Brownian motion, but with a larger variance this time. But maybe then when you zoom out far enough, you see another lattice with another cellular flow like this, and that will boost you again. And then imagine that you keep getting a boost from this vector field across larger and larger scales, but actually you get a boost across infinitely many scales, because every time you go to a larger scale, there's another boost. And the sum of all the boosts is not summable, so you diverge. And that, let me close this. So that is what causes now how do I go to full screen? That is what causes the superdiffusion. The superdiffusion is caused by kind of an infinite cascade across all the scales of the diffusion getting boosted again and again. And so the original fire you lit with this randomness, but then this vector field, which is nice and smooth seemingly, amplifies this chaos until the chaos just explodes and becomes super large. Okay? So we want to figure out a way to say that. In this particular example, you saw that there wasn't much the particles were doing until they got into kind of a boundary layer, near the edges of the square, and then they would kind of do a big walk. And so that's what happens in this model. Essentially, the diffusion does nothing inside the center of those squares, and then when it gets to the edges, it goes really fast. And that looks like a much larger a random walk. And what happens if you start with the original diffusivity as being nu, then what you end up with after just one of these scales is square root of nu. So you have a much, if you started off 10 to the minus 14, now you're 10 to the minus 7. It's really a much bigger boost. Okay? This exact thing is not what's going to happen in our model. It's a kind of intuition builder. Something like that is going to happen. It's just not quite so dramatic as this periodic example. Okay? Okay. So there are two kinds of things that you can try to prove. You can try to prove the double expectation of the particle's position is t squared of log t. Or you can prove that P almost surely that with respect to the vector field, you have the same behavior. Okay, now if you can prove the bottom one, you probably can take the expectation of it and get the top one, and that's indeed the case. Notice that the top one doesn't really have the same physical picture as the bottom one, because the bottom one is about a variance, an uncertainty in where the particle is. This one is about no such thing, okay? Necessarily. It might be, but it doesn't prove it. Because, for example, the top one can be true kind of for trivial reasons. For instance, suppose my vector field is constant. Constant, like in the E1 direction. Okay? Or let's say constant in a random direction, a completely random direction chosen on the unit sphere. Okay? Then the double expectation of this process by symmetry is 0, because just everything is symmetric. However, if you compute the thing now on the first line, which is maybe the annealed variance, it won't be t squared of log t, it'll be t squared. Because whatever constant you pick, now you're just going to push the particle at a linear speed. The Brownian motion won't really do anything. The particle will just move at a linear speed in the constant direction. And so when you square it, you'll get t squared. So you can say that's very superdiffusive. But it's not really superdiffusive at all, because the particle is just going to move in a straight line, and the uncertainty in its position is still square root of nu t, 2 nu t. So there's not really any uncertainty in where the particle is. So that number up there can be big, and but it doesn't really mean there's any superdiffusion. So this is sort of not what the physicists meant. But this caused a lot of confusion. The mathematicians that were studying this didn't just think that this picture was silly. They actually thought that this picture was what was happening in the problem that we're studying when p is equal to 2. Is they thought that what happens is the particle is going to follow long streamlines in this random sort of field. And once in a while, the origin will be just by luck near a streamline that goes very far away. And if that happens, the particle goes really far away, much, much further maybe than this, maybe t squared. But that happens so rarely that by the time you take the expectation, you get this log correction. And that's what they said. They said that this is what we think is happening. But the physicists actually predicted the quenched result. And the mathematicians that were proving results on this for the last 10 years and even very recently said, no, we don't think that's true, and they said it in public. Okay, so this has been a kind of controversy. So here are the results that were proved up until our work. So we have gradually sort of improving results. So in this case, Ola and Komorowski studied the case p less than 2. So they sort of assumed that there's a lot of noise, and using the lot of noise that they have sort of an exponent of super diffusion, but the exponent is not the one that that the physicists would predict. So this is a kind of result where they assumed a lot and proved a little, but the little is still super diffusive by a power. But it's in this sort of double expectation sense. The reason, by the way, that you can prove these theorems more easily is because if you assume the field is Gaussian, then you can do some kind of exact calculations that very often the physicists do as well. So then in more recent years, there's been kind of a series of papers that get, in the critical case, p is equal to 2 in dimension 2, improve the results until we have the predicted result of t squared of log t. I divide this by t. So they prove for the first quantity here this behavior, okay, which is consistent with superdiffusion, but not really proving superdiffusion, because it doesn't itself prove that the variance is actually getting large, just that this quantity is, okay. So that was the status. I skipped this one. I thought I deleted that slide. So our result is as follows. We prove that, okay, so I think it's hard to read this because the parentheses are going everywhere, but This thing here, I'll first look at this term. This is so this is all in the case that p is equal to 2. And I think this is even stated in dimension 2. No, it's in every dimension, but it's the exponent p is equal to 2. And this p is a different p. This is just an exponent. Okay? So we're looking at the pth moment of this random variable. So this expectation is taken with respect to the field, okay? And everything inside are these quantities that don't have, that depend on f, okay? This one is the first moment squared. So that's kind of, if you want, the displacement in how far you expect the particle to go just by, just because the vector field is pushing it in one direction. And, okay, and then we also have the difference between the variance and t log t times a particular constant. So our theorem doesn't just say it scales like this. Our theorem says it scales like this times a very particular constant, and the constant is independent of the realization of the vector field. So no matter what vector field you get with your dice roll, this thing will always be the same up to a constant. Okay? Now, how should you see this? The constant, I divided by t so that the thing is square root of log t, and over on the right-hand side is a 4th root of log t, more or less. So this is the leading order behavior, and this is smaller. And so the error between the variance and this constant is small, but also the second moment, so you know that if you wanted to have back just the quantity without this thing, you could triangle inequality and get it back, so that this implies the other result. But also even with all the powers p. Okay? Moreover, we proved that if you take the diffusion process and you zoom out, multiply by a special large constant, which is the log of epsilon squared to the minus a 4th, this will look like a Brownian motion. It converges in law in the space of paths of trajectories to a Brownian motion. So not only do you have the how far away, like what's the uncertainty in the particle's position, but you actually have the full law of the particle. It looks like another Brownian motion. Okay? Any questions?
Could you say more about the assumptions on f? So how did you build f so that this becomes true?
Okay, so this f is a, so let me go back. So our theorem is very general and can handle whatever f. The case that everyone was interested in was the case when f is the grad perp of the Gaussian free field in 2D. Okay? So it's a very natural object because if you just took white noise and then took away the gradient part by projecting it onto this, if you want to ask yourself, what is a natural, incompressible random vector field? Then one way to do it is to take a kind of random object like white noise, which is very canonical, and then project it onto the space of divergence-free fields. When you project that onto the space of potential fields, you get the Gaussian free field, which is a very natural object the probabilists and the physicists have studied for many years. And if you project it on the space of incompressible fields, which is like the kind of orthogonal complement of that, you get this object. And so that's the object that they wanted to study. For us, it doesn't matter that it's this particular object or that the dimension is 2. What you need is that f has correlations that decay like this with p equal to 2. Okay? And is, for example, Gaussian. If it's not Gaussian, then you have to add a technical assumption about the moments of the f or whatever, but essentially you want that the covariances decay like that with a p exactly equal to 2. So I don't write the full theorem because the full theorem would take, there's 5, the assumptions take half a page to actually state properly, but that's the reason for that. Okay, any other questions? Okay, so some comments on I've already said some of the comments, but so the result is the first quenched result. Again, many of the people working on this did not believe the quenched result was true. Even after our paper came out, they didn't believe it was true, and so it caused a stir, and people were trying to disprove our result for a while, and they posted papers on the archive announcing that they had not quite disproved our result. They had proved a result that was in contrast to, but not exactly in contradiction to our result, and there were comments like this. But now I think it's more accepted because there have been other papers that sort of use our strategy of proof on a different model and get exactly the same result. with down to all of the features, such as the fact that this, if you divide by t squared of log t, you get a constant, and it doesn't depend on the realization of the vector field. So this kind of universality result, I think, wasn't even predicted by the physicists. And I believe our result is actually sharp in the quantitative. The error that you get, which is the fourth root of log t, we believe that that fourth root of log t is really there, up to this little delta. I mean, probably you can remove the delta, but we think that that's actually there. And our method, you could imagine using our method to kind of go to next order and compute this thing and try to ask questions about it. We think that while the leading order term, which is this constant, is deterministic, the next order terms are going to be random again, and they're going to be complicated to analyze. The C star here, it should be pointed out, not only does it not depend on F, it doesn't depend on the diffusivity, which is a surprise. You would imagine that it would depend on the nu, but it doesn't. What matters is there is some nu there, so that you can start the fire. And once the fire is burning, it burns at the same rate. It doesn't care how big the match was that you lit it with. Okay? And that was also a surprise. We can compute, so in the case that people care about when it's the GFF, we know what the C star is. It's 1 over 2 pi. So there's just an exact calculation you can do, because the way that our proof works is it kind of shoehorns the problem into a perturbative regime, and then you can compute everything. Once you're in the perturbative regime. So we kind of make the problem into what the physicists were doing when they were doing their back of the envelope calculations. And then we can actually make, essentially we're making the physicist argument as we understand it rigorous. Okay, so the thing that we've been working on for a while, which is not probably another month or two to be out, because we can probably work on this the rest of our lives, is the case when p is less than 2. So when p is less than 2, you have a much more serious challenge with your analysis, because this problem, by the way, this theorem, we prove with some sort of renormalization group argument. But the renormalization group argument has a little bit of an advantage, because as you zoom out to large scales, the problem is becoming like the randomness is in effect getting smaller, and you don't have a true kind of random fractal. So you can use that in some ways to make the problem easier to analyze. In this case, when p is less than 2, the vector field really looks like a fractal, in the sense that no matter what scale you zoom out at, the solution will look the same. Okay? And the vector field looks the same, but the solution looks the same. So you have a kind of multiplicative fractal, and this becomes very, very difficult to analyze. Okay? So we spent a long time on this. What we get is we get the physicist prediction. There's a prefactor of gamma to the -1/2. And I think there might be a constant in front of here, which is again C star, but I dropped it. So it should really be C star times 2 times gamma inside of the -1/2, but I just dropped it. And you have this superdiffusive a factor of t here. And this is interesting. The exponent we get here is this only works when this parameter gamma is very, very small, because our argument is a kind of perturbative renormalization group argument. And so p has to be 1.99999, for it to work. But if you could get the gamma to be 4 over 3, so that somehow the p was 2/3, you would be in the physical regime of a turbulent fluid. And then if you plug in gamma equals 4/3 into that, you get exactly the Richardson 4/3 law in turbulent fluids. So you get which predicts that if you put if you look at how pollution spreads out of a smokestack, the variance at time t scales like t cubed. So you plug in gamma equals 4/3, you get t cubed. Okay, and that's the Richardson dispersion relation. Now, if I was a physicist, what I would say is, look, I made the result rigorous when gamma is 10 to the minus 200. Therefore, I plug in gamma equals 4/3, and I've explained turbulence, but no. So we're very, very, very far, and it's hard to imagine how we'll ever get out of this regime. But I think the physicists are also in that regime as well. So this is our kind of paper that's going to come out someday. All right, so now I'm going to try to explain in the last 15, 20 minutes how the proof is working and how we're thinking about the problem and how what the challenges are in making the proof work. Actually, I meant to say, are there any questions about the statements or anything? No. Okay. So we don't actually think about the diffusion process. We think about the generator of the process, which is, in this case of this, this SDE, is a second order elliptic operator. So it looks like this when you first write it. Laplacian u plus f dot grad u. Okay? Now, the sign of the f sometimes I think in the stock starts to change to minus f, but so just ignore the, what matters is that you have a Laplacian of u and you have this drift term. Okay? And in principle, I can understand the diffusion process completely if I can understand this operator. And I want to understand the diffusion process on large scales, and that means understanding this operator on large scales. Okay, so if I can do that, then I can somehow translate I can prove results on this PDE side and then translate them, and they'll give me what I want to know about the process. And that's how we do it. We never touch the process until we're like pulling corollaries out of our theorems. Okay, it's just all analysis on this PDE side. And the passage from the PDE to the process or going the other way is completely quantitative, and there's no problem. So all of the difficulty in the problem is really here, if that's how you want to think of it. So in our setting, I said that if you multiply by this small constant, so you look at the diffusion process under its normal parabolic scaling, and you mess up the parabolic scaling a little bit by, instead of epsilon, you divide by this big number, then you'll get this Brownian motion. What this means is that, okay, so I kind of want to get rid of the C star, maybe assume C star is 1 or something. But it means that at the level of the operators, if you take if you look at the generator, so here I'm scaling my diffusion process, so I need to scale my operator, which ends up doing that. This scaling makes this happen. Then if I multiply by this constant, I should get that this kind of converges to the Laplacian. Okay, that this elliptic operator, in some sort of coarse-grained sense on large scales, looks like this one. Okay, that's what I want to prove. And this is where my coarse-graining picture is going to come, because the whole proof is about somehow coarse-graining this right. If you don't want to introduce this like weird parameter epsilon, which isn't really there, then you can go to the original scaling and say that this operator is close to this operator. This is a very vague way to say it, okay? But you don't want me to say it precisely, I can assure you. This operator is close to this operator, where I have to multiply by this large constant, square root of log r, because that's the new diffusion. Okay? I think I wrote this right. Yeah, okay. And close to means somehow in the sense of homogenization. Like we're going to show that that in certain precise senses, I can, instead of looking at this, look at this. Okay? And what it basically means is this. Because this equation, this vector field, has many, many length scales, many, many wiggles living at different scales, the solution is going to inherit that property. The solution will have many, many wiggles on those same scales. What would I do if I just mollified the solution? I would like to mollify the solution at a certain scale, which has the effect of just destroying all the small scale wiggles and just kind of just getting rid of them at the scale of the mollifier. Okay? And then you can ask, does that mollified solution solve an equation? No, because you mollified the solution. You can't plug it back into the PDE. I mean, you can try to plug it back into the PDE, but it's going to be a mess, and you're going to have crazy error terms that it's not helpful. But we're able to show that, yes, actually, the mollified solution looks like a solution of this up to an error that we can control. Okay? If you mollify the solution, then you get a solution of the Laplacian. Okay, so that's what we're going to show. So now let me set up the problem, because I don't like having this vector field here. I like this. Okay, so I'm going to now cram the problem and force it to be of this form and get the vector field into the divergence form matrix, whether it wants to be there or not. Okay, so the way that this is what the physicists do as well, by the way. In 2D, right, we were already drawing these pictures with like streamlines. In 2D, if you have a divergence-free vector field, it's the grad perp of something. And this is called the stream function for that thing. In 3D, as you know from if you've ever had electromagnetism or whatever, you know that if you have a divergence-free vector field, you can write it as the vector potential of some vector field. In arbitrary dimension, the correct thing to do is to say, and there's probably a more correct thing to do, but if you know about differential forms, but I sort of stubbornly don't want to learn about that. If you have a divergence-free vector field, you can write it as the divergence, the row divergence, for example, of a skew-symmetric matrix field. Okay? And this is actually generalizing both of these cases. So you have a skew-symmetric matrix field, so that if you take the row divergence, a divergence of the rows, and you make a vector field out of that, first of all, it's automatically divergence-free, because if you do a double divergence, it vanishes by skew symmetry. But it turns out that any skew-symmetric matrix can be written like this. It's like so this is like a potential for that thing. Now, so instead of the operator being like this, I can take this part, and I can write it like divergence, like let's say there's a u here. I can write this as divergence of k grad u. And it looks like there's too many derivatives now on u, but there's not, because when the derivative falls on the u, it makes a Hessian, which is symmetric, and it contracts against the skew-symmetric k, it dies. Or I guess I'm calling it m now. Yeah, m. It contracts against the skew-symmetric m, and it dies. Whereas when the divergence hits the m, it makes the f. And that's why I can write it like that. And therefore, I can take the whole thing, and I can write it like divergence of nu identity matrix plus m grad u. And you see that I have my A. My A just is, all the interesting part of the A is in the skew-symmetric part. And what we're going to show is that as you coarse grain this guy, the skew-symmetric guy gets coarse-grained away, and it increases this. So when you coarse-grain a skew-symmetric field, it becomes symmetric. And it actually is positive, and so it's going to increase that nu. And because I'm assuming I have like isotropy, when you coarse-grain it, it just increases, it just becomes a scalar, and it increases the scalar. And we're going to sort of do a scale-by-scale proof where we integrate away the small scales in the m, sort of gradually getting rid of the skew-symmetric scales, one scale at a time, starting from the small scales, where the, starting from the scale where this is sort of the, where that randomness lives, until we have integrated away all the randomness. Okay, so this is what I said on the slide. We can write the generator like this. Okay, so now we're in the kind of problem I like. And so now I've got the problem into the place I like, and now I'm going to coarse grain it. Okay, so maybe I skipped the sort of overview slides about what coarse graining is, and just kind of try to describe how our method is actually working. I did want to show this slide, which is that when you have a lot of attempts to formalize, coarse graining, or formalize, thermodynamic limits. Maybe you have a cloud of particles and you want to show it converges to a measure or something like that. Many times when you do this, the thing you're coarse graining is itself a physical measurable quantity, and therefore when you coarse grain it, you really are just averaging. So like if you want to show a cloud of particles converges to some measure, you usually mean, I'm going to look at the number of particles in a box and count them, and then that's going to be the coarse-grained, object. But when you have an elliptic equation like this and you want to coarse-grain this field, you don't do that, because this thing, this A of x, is not something you can measure directly. The things that you can measure are like the gradient of u and the flux of u. Like you can measure the flux of the electric field, and you can measure the electric potential, but you can't measure directly the constitutive constant that relates them. You have to measure them both and then divide. And so because of that, those fields don't get coarse-grained by just averaging. And so and that's what makes kind of homogenization of PDE kind of non-trivial. And it's what makes it hard. Okay, and so there's not a lot of theories of coarse graining that are part of rigorous mathematics that can handle that. And it turns out that a lot of fields fit this exact setup. So if you talk about diffusivity, conductivity, viscosity, and in quantum field theory, or just in Euclidean field theory even, there's inverse temperature that you sometimes need to renormalize. These things are all really diffusivities in my language. They're all in A of x. Okay? Anyway, the hard part from the point of view of analysis is coming up with some coarse graining scheme which gives you closure, so that you can, you've got, if you're going to go across an infinite number of scales to make this theorem, and because we have a true superdiffusion, it means that it arises because we have summed little boosts to the diffusivity across many scales. And if that's what's causing superdiffusion, then you have to have an infinite number of scales to do it, which means you have to have an induction argument, which means your induction has to close, right? If you only had to go across 5 scales, you could kind of come up with ad hoc arguments that handles the scales one at a time, and you'd be done. But if you have to do an infinite number of scales, you really have to come up with an argument that closes. The assumptions have to then give you a conclusion, which is the assumption at the next scale, and that's what's difficult, because when you start to kind of blur away the details, you feel like you lose information. So your argument has to somehow not look at the small scales. Okay, so how do we do it? The results I'm presenting here rely on a paper that we've been working on with Tuomo for a while, that was finally published, but was written a couple of years ago. And it actually relies on our approach to homogenization from 10 years ago, which we've gradually been improving to the point now where we can kind of solve the closure problem, where we can make a genuine scale-by-scale induction that can go across infinitely many scales. Okay, and which doesn't, for example, require strong assumptions of ellipticity. Like, we don't need the assumption of uniform ellipticity, which is commonly used. Okay, so how does it work? We look at the field. For every block, or just cube, we define 2 matrices, A and A star, and these are our coarse-grained matrices. I'm going to describe the setup in the case when A is symmetric, even though my main application is the case where it's very not symmetric. And I'm going to do that because the skew-symmetric case is harder to describe, but the same basic story is intact, okay? So we define these matrices at every block. So we define it like in blocks like this, but then we also define it in smaller blocks and in smaller blocks, and the block size goes to the infinitesimal scale. Okay, so we keep track of all the blocks. In the same way that you build a Bezoff type norm in functional analysis or whatever, or you can build it, it's kind of like Littlewood-Paley out of such blocks, right? You look at the average of the function maybe on blocks of all sizes, and you somehow sum them and incorporate them into a norm. We're going to do exactly the same, and our way of doing it is going to resemble a negative regularity Bezoff type norm. Okay? But instead of looking at the average of the field, we look at these coarse-grained quantities, which are very much not the average of the field. Okay, and that reflects the fact that what I was saying about this A of x not being measurable by a physical experiment. Okay? So anyway, we developed this general analytic framework, and one of the main steps is to develop elliptic regularity, and the whole theory of kind of elliptic theory under this coarse graining framework. So, because we need to use elliptic estimates in our proofs, but we need to not use any information about the small scale, which means we cannot use information about A of x. In particular, we cannot use information about the ellipticity constants. So we have to come up with coarse-grained ellipticity constants and show that we can get all the same estimates that you can get in elliptic regularity in this coarse-grained way. Okay? Let me show you, let me see, so I'm going to run out of time pretty soon. Let me try to show you what happens in this particular problem, okay? And how you could imagine seeing I can't explain everything, so what I'll explain is why in this problem one scale will enhance this by a little bit, and how you can turn that picture into a kind of like ODE for the effective diffusion in the scale parameter, which is, and then sort of integrate that ODE to guess the scaling of square root of log t. So that's what I'll show. So what happens is you want, and maybe I'll go to the next slide first. So what you do is you assume that your m, this m that I made out of the vector field, can be decomposed into scales like this. Okay, so I just want to split its frequencies. It's almost like a Fourier decomposition, but it's in physical space. So I split it as a sum of a bunch of waves with wavelength 3 to the n, and I sum over all n. This sum doesn't converge, but that's okay. Okay, because I'm giving a formal idea. This is what you do all the time in topics like this. These things are all skew symmetric, and maybe they have the same law, and you're just scaling them. In particular, all their sizes are of order 1. Okay? And so what I'm going to do is I'm going to gradually sort of integrate out. I'm going to try to start the sum at a larger and larger integer and kind of get rid of these small scales. Okay? So here's how it works. The full operator is here, and I want to show that in this range of scales, so now I'm zoomed out to a scale where the scale is 3 to the m, and I'm going to look, okay, I'm going to have a kind of window of scales that I'm going to look at. So it's 3 to the m to 3 to the m plus some small increment. So you should think about m as being very big and n naught as being like 12. Okay, so it's scales between 3 to the m and 3 to the m plus 6. Okay, and I want to show that this is looking like divergence of, this thing is a scalar matrix, so you could think of it as a number or a multiple of the identity matrix. And this here is the m, but where the sum only starts at, it's the boldface m, the skew symmetric matrix, where the sum only starts at scale m minus 1. So I've somehow integrated out all the scales below that. And so I'm only summing from m plus 1 to m plus this n naught. So I have so it's like I only see the waves in the m on this range of scales. All the waves below that have been dealt with, and the net effect of them have been put in here into this S bar. Okay? So that's what I somehow proved, or this is my induction assumption, if you want, like if I could ever prove this. Then what I could do is say, well, suppose I knew also, maybe by induction hypothesis, that this S bar m is large. Okay? There's only n naught many terms here, so 12. If this is large, and this is of order 12, then I can treat this perturbatively as like a perturbation of that. So I can reduce to the case when the skew symmetric guy is a perturbation by virtue of the fact that as I renormalize, my diffusion matrix is growing. So you have to somehow coarse grain the system until this is large. Once this is large, this is small, and then boop, you can treat it like a perturbation. Okay, and so that's what we do. And then if you can treat this like a perturbation, you can then guess what would happen if you homogenized it, if you took it and put it into the S bar m so as to increment the S bar m to S bar m plus n naught. And what you get is just by an easy calculation, because if this thing here is a constant, so the main part of the operator is now a Laplacian, and this disorder is small, and so you can kind of just guess what the increment should be by inverting the Laplacian on this and ignoring the kind of second order quadratic term. And that should arise. And you can in like half a page just compute this. And you get that the S bar m plus n naught should be S bar m plus something here, plus a constant. And the constant is really some special constant which has to do with what this thing is doing, times log 3. I just sort of normalized the constant by log 3 because the scales are powers of 3. N naught, the number of scales, but then you divide by S bar m because the effect of the drift, the effect of the enhancement is lessened by the fact that it's smaller in size relative to that. So you basically get this recurrence relation that says S bar m plus 1 is S bar m plus a constant divided by S bar m. That's basically what you get. And if you look at that for a second, you say, okay, this should be some sort of power of log. If this was not here and it was just S bar m plus 1 equals S bar m plus c, then this would be easy to solve, right? It would be c times m. And since m is the logarithm of the scale, you would get constant log of the scale. But because I'm dividing by it, it should be a bit less. And so what you do is you look at this recurrence relation for like 3 minutes. You can give it to your undergraduate students and ask them to solve it, and you'll get square root of m. It scales like square root of m. And that's the reason that, so you get square root of m times a constant that you can compute, and this is the reason for the square root of log r. So all of our coarse-graining theory, which I didn't have time to explain, somehow is about making this little squiggly rigorous in a way where you can actually make it into an induction argument across all the scales. So to explain that would take a much longer time, so maybe I won't attempt it. I have some slides here. If you want to ask me for my slides, there's some stuff about the proof here, blah, 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 but I'll stop there. Thank you for your attention.